Hey, Nathan here. Welcome back to another MonoGame Advanced video. In the last video we discussed scaling objects, where we scaled them by a single float value and where we converted that to a vector2 format to where we scaled both x and y the same value. In this video we are going to extend those concepts. We're still going to use that when we draw our object. But what we want to do is manipulate our rectangle, and in order to do that, we need to create a translation matrix to where we can appropriately create a bounding box on a scaled and rotated object. So let's get started. In the sprite.cs file, at the top where we have our private fields, at the bottom of that list, let's add a private matrix, and that's a 4x4 matrix. If you've seen my game math videos, that is what we are using. The game math videos should be released with this video as well. So I'm going to call this underscore transform. Okay, so anytime our position changes, our origin changes, our rotation changes, and our scaling changes, we need to update our bounding box, and we need to update our translation matrix in order to do that. So anywhere we change those, we need to change our matrix. So as you might imagine, we might need to call that in several places. And one of the things that you should never do is code repetition unless you're calling a method. You don't want to redo matrix transforms 5 different times. You just want to call one method that does it once. Now you can call that method 5 times, but you don't want to actually do the operations 5 times. So between on content loaded and update rectangle, let's add a private void update transform matrix. It's just going to be a void method, and it's not going to have any parameters. So private void update transform matrix. Now, the standard way you want to deal with matrices, transform matrices in general, is to do it as a SRT basis. That means scale times rotation times translation. You always want to do translation last. So the standard procedure is SRT, where it's going to scale, then rotate, then translate to a specific position. The reason we do translation last is because scale and rotation operate based off of the 0 point, the center of the axis. Now, take a look at what we have here. Origin. Remember when we discussed the position and when we discuss origin, your position value is dependent on the origin. We have a vector2, 0. That's different if the origin is the top left of the sprite, the center of the sprite, or the bottom right of the sprite. So our position is based off the origin. Scale and rotation operate at the center point of the axis. So what we need to do is reverse the origin if it's present. So we reverse the origin. That way, scale and rotation operate in the most absolute center of the axis as possible. Then we translate. So we're still doing SRT, but we need to reverse the origin first, because our origin shifts our position values over and down. So what we need to do is generate underscore transform is equal to matrix dot create translation. So we need to reverse the translation of the origin. New vector 3, the negative underscore origin, we need to reverse the origin, comma 0. The matrices work in a vector 3 environment. So we need to convert a vector 2 to a vector 3, and that's why we provide new vector 3, where we provide the vector 2 and then just the third component. Alright, so we reverse the translation. We reverse the origin. Now we need to scale it. Matrix.create scale. That's going to be underscore angle. No, I'm sorry. That's scale. Angle's coming up. So we're going to create the scale based off the scale value. And that scale is a vector 2. So what we need to do is create another private field, float underscore scale value. That will hold the single float value and just update it based on what you provide into the constructor. So that we need to have that as a single float value, so underscore scale value. We cannot use the vector 2 for the create scale call. It has to be a single float. So just keep a copy of that on what you provide in the constructor. That way we can use that in our transform matrix calculation. Now the fun part, which is create rotation Z underscore angle. Alright, so why Z? I'm going to throw up a video overlay, but I'm also going to discuss this as I'm working on it because I have to do the video overlay after the fact. Alright, imagine you have a book or your phone in front of you. Everything's upright. You're looking at the front of the book in front of the phone. The screen's facing you. The front of the book is facing you. All the text and everything is right side up. You're not reading upside down. So everything is like it should be. Rotation Z. Imagine you take the phone or the book and you're holding it in one hand and you grab it from the other hand and just rotate it in place. So now the text is upside down. It's still facing forward. The front of the book or front of the phone is still facing you, but everything is upside down. Then you can rotate it again 180 degrees, and now it's back to where it was. So that is what we want a 2D game object to do, is rotate that way, either clockwise or counterclockwise. But we want it to rotate that same way that we've just demonstrated. That is what a 2D object should be rotated by. Now, why not rotation Y? So imagine you have your phone or your book in front of you. The front of the book or front of the phone's facing you. Everything's upright. Now, on your other hand, just rotate it to where you see the side of the book or the side of the phone. If you're using a book, it will be like you're putting it in a bookshelf. So you want that label of the book out. So you see the small label on the side of the book, and it's facing you. If you're looking at your phone, it's usually the volume controls with the vibrate, mute, toggle switch, or the button that turns it on or off on the side of the phone. Now keep on going that same direction, and then you're looking at the back of the phone. And you do it one more time, and you're looking on the other side. If you're looking at the book, it'll just be a side view of all the pages. If you're looking at the phone, it's more buttons or whatever you have on the other side. Not all phones have side controls on both sides. Do it one more time. Now you're looking at the front of the phone or front of the book again. So that's the y-axis. The x-axis is you take your phone or your book and rotate it to where you're looking at the bottom edge. If you're looking at a book, it's just the bottom view of the pages, so you just see the bottom side of the pages. If you're looking at your phone, it's usually the port where you provide your power, your USB, micro USB, lightning cable if it's an iPhone, and your headphone port where you put your headphones in, usually. And then if you keep on going, you're looking at the back of the phone or back of the book, and all the text is upside down. Now, if you do it one more time, you're looking at the top of the book, top of the phone, and some phones might have the headphone jack on the top, so that's where you would see that. On the book, it's another view of the pages. And then do it one more time, you're looking at the front of the phone or front of the book where everything is right side up. So that is the x-axis. So the z-axis is what we want. You rotate it by the z-axis. That just rotates the object clockwise or counterclockwise. Keeping it in place, just rotate it clockwise or counterclockwise. Alright, that's a quick overview on why we do Z, even though it's a 2D game. Alright, SRT, we reverse the origin so we can operate in a zero-base environment for scale and rotation. And now we need to translate it based on the position. Matrix.create translation, new vector 3 underscore position, comma 0, and there we go. So that is our transform matrix. Remember to do it in SRT. If you have origin, or if you're pushing your position value by any other factors, you need to reverse that. You need to go back to square one, scale, rotate, then translate. Okay. Update rectangle. Update rectangle. This is going to change, so delete everything. So we're still going to use a float value to scale. Actually, a vector 2 value to scale because we can scale x and y differently. And we're just going to use a single float value to rotate. But we want to update the rectangle. We want to update the bounding rectangle based on how we're scaling and how we're rotating. That way, the bounding rectangle is wrapped around the texture, no matter how big it is or how small it is, or what the angle is. We want it to be the bounding rectangle, so it will be on the outside edges of all possible corners of that texture. That way we will get an appropriate rectangular collision detection. So this is where it will get a little bit tricky. We are eventually going to scale, rotate, and translate. So what we need to do is we need to calculate a zero-based rectangle, and we need to translate that based on our transform matrix. Well, not just translate, rotate, and scale. So we need to do all those operations on a zero-based rectangle. The reason we're doing it in zero-based is because we're doing all these other operations to it. We don't want to put the rectangle in the position value because it's going to be translated by that position again. So we want to operate it in a zero-based environment as well. So what will the rectangle be? That will just be 0, 0 for the x and y. It's going to be based off the 0 position. And then a rectangle is just the width of the rectangle is the texture's width, and the height of the rectangle is the texture's height. So the rectangle is going to be 0, 0, texture.width, texture.height. And we have 4 corners of a rectangle: top left, top right, bottom left, and bottom right. We need to convert all those points. We need to transform all those points by our matrix we created above, and then we'll get a brand new rectangle based off those values. So we can do this by using vector 2's, which will make things a lot easier. Vector 2, top left. So the top left of our rectangle is equal to vector 2.transform. We're going to transform a vector by our transform matrix. So the top left of our rectangle is going to be vector 2.0. We're working on it based off of the 0 by 0 position. Underscore transform for our matrix. So that's going to transform our top left coordinate of our rectangle. Vector 2 top right is equal to vector 2.transform. New vector 2, the top right is going to be underscore texture dot width, comma 0. And we're going to provide underscore transform for the matrix. Vector 2 bottom left is equal to vector 2.transform new vector 2 0 comma underscore texture dot height, and provide underscore transform for the matrix. Vector 2 bottom right is equal to vector 2 dot transform new vector 2 underscore texture dot width underscore texture dot height, underscore transform for the matrix. So for those that know the rectangle coordinates based off of our texture value, this will make sense. We are not using our position, we're not using our origin, we are working on it in a 0 base. We're going to put the rectangle at position 0. Now a rectangle only expands to our texture. So 0, 0, texture dot width and texture dot height. That is our rectangle. And 4 corners, now we're going to transform those 4 corners. Okay. Now we need to get the minimum x, minimum y, maximum x, and maximum y. Why do we need to do that? We need to get the minimum x, that's the left edge of the rectangle. We need to get the minimum y, that's the top edge of the rectangle. We need to get the maximum x, that's the right side of our rectangle. We need to get the maximum y, that is the bottom edge of the rectangle. So min x is left, min y is top, max x is right, and max y is bottom. All 4 sides make a rectangle. I added a MathEX class, and it just provides minimum and maximum, and we provide float values, float array values as a params. So we call minimum, we can just call 1, 2, 3, 4, 5, on and on and on and on, and it will get the values dot min. It will get the minimum value based off that array. And then it will get the maximum similarly with the max method. So just add a public static class. I like to call it the what I'm extending, so math, and then EX for the to identify that it's extending the math functions, the functionality of mathematics. And then a public static float, it's going to return 1 float value, the minimum, and then inside the parentheses, params, a float array, and then I call it values. And then it returns min. Same thing with max. So let's go back to the sprite class. And let's go ahead and do that. Vector 2 min is equal to new vector 2. So we need to get the minimum of all the x's and then the minimum of all the y's. So mathEX.min top left dot x, top right dot x, bottom left dot x, bottom right dot x. So that's the minimum of the x. Now we need to get the minimum of the y. Math ex dot min top left dot y, top right dot y, bottom left dot y, bottom right dot y. Alright, so I'm actually going to copy these two lines here, and I'm going to paste them below. And I'm going to change that from vector to min to vector to max. And I'm going to change mathex.min to mathex.max. Same thing with the second line. Change mathex.min to mathex.max. That's all we need to change. So once we have the min x, min y, max x, and max y, we can generate our rectangle. Now these are float values. We are using vector 2 here, so each component is going to be float. Our rectangle needs to have integers, so we need to cast everything as integers. Int min.x, alright? Int min.y. Alright. Now, max x and max y are the location values of those sides. We need to convert those to the width and the height of our rectangle. So we need to cast this as an int, opening parentheses, max.x minus min.x. So that will give us a width. Now we need to do the same thing with the y. Max.y minus min.y. That will give us the height of our rectangle. So that is it for our updating rectangle. Now let's go to the update method. Like I said, anytime our position changes, our rotation changes, our scale changes, or our origin changes, we need to update our matrix. So that is why we created a method here. So inside this update method, before we update rectangle, we need to call update transform matrix. And if you remember, we in the onContentLoaded, we set up our origin, so that changed, but we did not call update transform matrix yet. So right before we update our rectangle, remember to call update transform matrix. So I'm calling update transform matrix from the onContentLoaded method as well as the update method. Alright, our per pixel collision is going to be severely broken at this point. It's going to actually throw exceptions in some cases. So let's remove everything and simply leave return false. Or actually, let's set return true so we can see if it's actually working. Alright, so per pixel collision, it's just going to return true. Our draw should be the same. Our debug sprite should be the same. Alright, let's press F5 and see what happens. There we go. As you can see, our rectangle is being scaled. And our collision is working. Now this is including the update where an object cannot leave the bounds of the screen. So that is why the big sprite on the right side is kind of jumping back and forth. So this it was actually 2 videos in one. We fixed our rectangular collision detection by just doing what we did was create a bounding rectangle based off our transform matrix that automatically fixed our rectangle collision detection, but we still need to fix our per pixel collision detection. So I'm going to press F5 and run it again. Those 4 dots, those are scaled and rotated and transformed. So now we have a correct bounding box of our object. It's a little hard to see on the sprite that's smaller, so I'm going to go to game1.cs and increase that from 0.1f to 0.4f. Just going to make it 4 times bigger. You can see the dots a little bit. Let me make it a little bit bigger. 0.6. There, you can see the dots a lot better on this sample. So as you can see, our bounding box is successfully wrapping around our texture. No matter what the scale is, no matter what the rotation is, it's controlling the outside edges of our texture. So that is it for this video. I hope you enjoyed it. Since this was a 2-in-1 video, the only one left we need to do is to fix per pixel collision detection. So there will not be a dedicated rectangular collision detection video for matrix transforms. The fact that we even did matrix transforms fixed our rectangular collision detection. One quick note, if we go to sprite.cs, we're still using the same scale value, which is a vector 2, and the same angle value, which is a float. But our bounding rectangle was manipulated by our transform matrix. So I hope to see you next time for the fix to per pixel collision detection using matrix transformations. Thanks for watching.